Welcome to the unit number 5, Ubiquitous Clouds and Internet of Things. In part 1, we have seen cloud trends in supporting ubiquitous computing, performance of distributed systems. So we will be seeing some part of cloud enabling technologies and performance related parameters or metrics for distributed systems in this particular part 2. We already talked about the various metrics which are being used for high performance computing or high throughput computing systems. In that, we have already seen system throughput, multitasking scalability, and we were actually looking at availability measures and then data security and the cost effectiveness. In continuation with the previous part 1, the system availability is referred to the percentage of time the system is up and running normally. This percentage reflects the effects of downtime after unexpected failures and scheduled maintenance for the software upgrades. System availability is defined by the ratio of MTTF to the sum of MTTF and MTTR applies to all the systems, wherein high availability specifies the performance level of a system with controlled downtime through quick recovery from failure. Basically, the availability is maintained sufficiently high with at least 5 nines, meaning that at most 5 minutes of downtime per year, wherein high availability cluster refers or could demand 99.99999% availability, meaning only 3 seconds of downtime per year is expected. So this is the biggest difference between system availability and high availability. Availability is affected by platform architecture, service models applied, system vulnerability, and resilience to network attacks. Cloud security is attributed to user confidentiality, data integrity, access control, firewalls, intrusion detection systems, defense capability against viruses or worm attacks, reputation systems, copyright protection, data lock-in, APIs, data center security policies, trust negotiation, and security auditing services. Trust among resource sites can be negotiated with non-conflicting security policies. To secure elastic resources, the reputation system should be designed to safeguard scattered resource sites and data centers. The security index is equal to the minimum number of sensors and actuators that need to be compromised by the attacker, such as to conduct a perfectly undetectable attack. The resource site security index delta and user access records should be maintained through periodic auditing. Next basic performance attributes is cost effectiveness. This refers to the estimate of an effective scale of economy achievable by a given system. The provider must pay the data center owner for the resources used even if they belong to the same company. Regardless of the cloud service model applied, the cost of cloud usage is primarily determined by the hours used. C is the hourly charge to the user by the provider. H is the number of service hours provided to the end user. Total income of the provider from the user payment of the service is calculated by provider cost equal to H multiplied by C. The total cost the provider paid to the data center is estimated by cost of D. D is data center. So cost to be provided to the data center is equal to H multiplied by the ratio of D to U. Here D is an hourly charge by the data center and U is the utilization rate of the data center resources. The cost effectiveness mu of the cloud service is measured for assessing the profit margin by the service provider. So this is a formula for cost effectiveness. Mu is equal to provider cost minus data center cost upon data center cost. So it equals to CU by D minus. So we have seen all the 5 basic performance measures. One of the compound measure is quality of service. So we will see the details of quality of service in cloud computing. Cumulative performance of a cloud platform by a compound metric is called quality of cloud services and denoted by theta. This metric measures the overall quality of the cloud service regardless of the particular service models being applied. A five-dimensional QoS graph is used to plot the aggregated cloud performance or to quantify the QoCs graphically. So each QoS graph has five orthogonal dimensions. These are the independent attributes: system efficiency, scalability, then availability, then security index, and then effective cost. So these are the five attributes which are basically independent attributes representing the five performance attributes for quality of service in cloud computing. The shaded area of QoS graph represents the cumulative strength or quality of the cloud service being provided. Let A of pentagon be the ideal operating area of the pentagon in QoS graph. The scale 0 is located at the center of the perfect pentagon, meaning the lowest values of the five performance parameters which are already known to you, like system efficiency, scalability, availability, security index, and cost effectiveness. So as per these five parameters which we have already discussed in previous slides, the combining all these five independent parameters, we have a compound metric known as QoCs, quality of cloud services. So the parameter value of 1 means the highest performance in each dimension of the measure. So theta, which is nothing but QoCs, is a ratio of shaded portion, which is actual operating area of the pentagon, to the ideal operating area of the pentagon. The lowest value of the theta measure means poor performance. The higher the value of theta toward 1 implies the higher performance. Next point is enabling technologies for Internet of Things. In ubiquitous computing, the Internet of Things provides a network of sensor or radio connected devices that can be uniquely identified and located in cyber physical space. The IoT is a natural extension of Internet. The foundation of the IoT is radio frequency identification. This enables the discovery of tagged objects and mobile devices by browsing an IP address or searching for a database entry. In the 19th century, computers learned to do as instructed. In 20th century, computers learned to think. And in 21st century, the computers want to learn how to perceive by sensing and understanding. Everyday objects include not only electronic devices but also objects such as humans, animals, food, clothing, homes, vehicles, commodities, trees, hills, and landmarks. The IoT system could greatly reduce the chances of a company running out of stock or wasting products, as all concerned parties would know exactly what products are needed. Misled items and physical theft would be affected by the fact that the location of an item would be known to all parties. So you can do the computing from anywhere, anytime, and track those items or things, as we have already discussed over here, all the objects, through the Internet of Things. Ubiquitous computing basically is a model of human computer interaction in which information processing is integrated into everyday objects and activities. For daily activities, people may engage in using many pervasive devices simultaneously. They may not even be aware of the existence of interactive devices. IoT cannot be realized without systems design and engineering and user interfaces. The IoT cannot be realized without system design and engineering and user interfaces. The human computer interaction models, whether command line, menu driven, or GUI based, are inappropriate to meet the ubiquitous computing demands. So, the contemporary devices that lend support to ubiquitous computing includes smartphones, tablet computers, sensor networks, RFID tags, smart tags, GPS devices, and others. We'll look into how the development of Internet of Things happens. In 2005, the concept of IoT entered in the limelight. The IoT should be designed to connect the world's objects in a sensory manner. The roadmap of IoT is shown in the figure to anticipate the desired technology advances to make the IoT reality in 25 years. If you see the timeline over here of 25 years, we will see how the technology has evolved or developed. So, in 2005, as previously we have seen, so RFID tags have been facilitated for inventory and loss prevention. So basically, the major demand was being in the logistics and inventory control, and to monitor the logistics and inventories. So after that, like basically it was being used in our supply chain management. Later on, the second wave of application has come into existence, wherein the IoT has picked up into. So surveillance, security, healthcare, transport, food safety, document management, etc. So we can call it as a vertical market application. Okay. So then after this, the when this in this second wave of application, there are some advanced applications like uh, the personal healthcare, which has in which there is a need to locate the people and everyday objects. So, ability of devices located indoors to receive the geolocation signals has been used in this kind of applications where the personal healthcare was of utmost importance or is of utmost importance. So, ubiquitous positioning is area of applications in which IoT or IoT devices were being used. Then the era of miniaturization, power efficient electronics, and available spectrum has been started, in which the various teleoperations and telepresence was the main aim, means the ability to monitor and control the objects which are remotely placed. So the objects which are available through internet or the physical world which is made available through web is actually been considered over here. There are some software agents and advanced sensor fusion is being thought of. There are some examples if you consider physical web. In the physical web, there are some examples wherein you can do the fleet management or the lost and found management kind of applications which will be available by the fusion of advanced sensors and the software agent. In enabling technologies for the Internet of Things, there are two kinds of technologies. One is enabling technologies for IoT and synergistic technologies for IoT. So we have machine to machine interfaces, protocols for electronic communication, microcontrollers, wireless communication, RFID, energy harvesting technologies, sensors and sensor networks, actuators, GPS, global positioning systems, and software engineering, which enabled IoT. We have some synergistic technologies like geotagging and geocaching, biometrics, machine vision, robotics, augmented reality, telepresence, then live recorders and personal black boxes, then tangible user interfaces, clean technologies, and mirror worlds. So these are the few two different kinds of technologies which are being used in IoT. One is the technology which enables the IoT, other technology which is synergistic for IoT. Architecture of the IoT. The IoT system is likely to have an event-driven architecture. IoT development is shown with a three-layer architecture. The top layer is formed by driven applications. The bottom layer represents various types of sensing devices, namely RFID tags, ZigBee, or other types of sensors, and road mapping GPS navigators. The sensing devices are locally or wide area connected in the form of RFID networks, sensor networks, and GPSs. Signals or information collected at these sensing devices are linked to the applications through the cloud computing platforms at the middle layer. The signal processing clouds are built over the mobile networks, the internet backbone, and various information networks at the middle layer. In the IoT, the service-oriented architecture model is adaptable. A large number of sensors and filters are used to collect the raw data. Various compute and storage clouds and grids are used to process the data and transform it into information and knowledge formats. The sensed information is used to put together a decision making system for intelligence applications. The middle layer is also considered as a semantic web or grid. So, this was the architecture which we are talking about. We have application layer, which is the top layer, in which there are different applications which are continuously communicating and transferring the data, accepting the data continuously through a cloud. This is the architecture which has three layers. One is application layer, another is network layer, and third one is sensing layer. So sensing layer basically is available on the objects, and whatever the data transmission needs to be done through RFID technology is being passed through the network layer and stored in cloud computing platform. From where this various different applications, IoT based applications, can take the advantage of this particular data which is being stored onto the cloud for and generated by this sensing layer, which is generated from the sensing layer. So this is a processing layer, this is a sensing layer, this is processing and networking layer, and this is an application layer. So the architecture of an IoT consisting of sensing devices that are connected to various applications via mobile networks, internet, and the processing clouds. We have various wireless networks which supports the ubiquitous computing. These are the various standards which are actually being used. ZigBee is the one which we have seen. Then we have in GSM technology which is used to connect mobile network. We have Wi-Fi 802.11, and then we have Bluetooth technologies which enables the IoT. Different properties of these supporting wireless networks is mentioned over here, and as per the requirement these different technologies are being used into applications. One of the example of how the technology is enabling the Internet of Things is basically shown over here. So there are many body sensor nodes which are available, like basically used for heart, used for chest, then used for sensors which are your wearable devices, you can say wristband, chest belt, etc. So these are the sensor nodes which are nothing but an actuators produce the data, and if you are into a hospital, so those are being through ZigBee compliant communications, those are being stored to the medical center server PC. Or if you are remotely available, then if you are at home, so then this data of the patient's mobile, this data of the patient, okay, is being sent through GSM via cellular network to the doctor's mobile phone, as well as it is being stored into the medical center server PC. So if the patient is in the hospital, so then the people from the hospital can look into the previous record, and record can be analyzed. If the doctor wants to view the data, then doctor can also view through his own personal digital assistants. So doctor can view the data, as well as the hospital administration also can receive the data for the analysis purpose. So basically this is how the measured data is being transferred to doctors and medical professionals using wireless sensor network. So the next point is innovative applications of the Internet of Things. There are major civilian applications which are being developed using IoT, as well as there are many military applications which are IoT based. So in general we'll be looking into three major domains. One is industry domain, other is environment, and third one is the society. So there are different examples in these three domains which is being summarized in this particular table. There are few specific wireless sensor based applications. military sensor networks to detect and gain as much information as possible about the enemy movements, explosions, and other phenomena of interest. There are sensor networks to detect and characterize chemical, biological, radiological, nuclear, and explosive attacks and materials. Another sensor networks to detect and monitor environmental changes in plains, forests, oceans, and so on. Wireless traffic sensor networks to monitor vehicle traffic on highways or in congested parts of a city. Wireless surveillance sensor networks for providing security in shopping malls, parking garages, and uh, other facilities. Wireless parking lot sensor networks to determine whether the lot is occupied or available. So these are the various different applications which are wireless sensor based application. Next application of Internet of Things is retailing and the supply chain management. The Internet of Things, retailing and the supply chain management. IoT applications will promote business, improve our society, and enhance economical growth. These include specific IoT applications in retailing and logistics services and supply chain management. Many industrial, government, and community services can benefit from these applications. So these include activities or initiatives to promote development of better and more efficient societies, cities, and governments. In the example of retailing and logistics services, we will see how the IoT has played a vital role. So emergence of RFID applications depends strongly on adoption of retailers, logistic organizations, and package delivery companies. So in particular, retailers may tag individual objects in order to solve a number of problems at once, like accurate inventorying, loss control, ability to support unattended walk-through point of sales terminals, ensuring or monitoring whether perishable materials are intact or need attention may entail communications among things, refrigeration systems, automated data logging systems, and human technicians. Supply chain management is a process used by the companies to ensure that their supply chain is efficient and cost effective. If you consider this figure over here, so basically there is a supplier and there is a consumer. So supplier basically manufactures the goods. This good is being received and unloaded at the distribution center. From the distribution center, the delivery is loaded and supplied to the retail stores. And from the retail stores, the consumer basically purchases the items required. Thus, on the basis of this, the store basically checks the availability of its inventories, and as well as it will forecast the required demands. Okay, so then the store generates the demands, and the stock is being ordered. Supplier basically delivers to the depot. So this is how the whole chain is being completed. So there are 5 stages in supply chain management. First is planning and coordination. Second is material and the equipment supplies. Next is manufacturing and the testing. Fourth is delivery of products. And fifth is after sales service and returns. IoT basically being used, making the supply chain efficient and the cost effective. Next innovative application of the Internet of Things is smart power grid and the smart buildings. Environmental protection is a global issue. Green energy is desired to save energy and to reduce the effects of global warming. The smart grid is made possible by applying sensing, measurement, and control devices to electricity production, transmission, distribution, and consumption. So, a smart power grid basically includes an intelligent monitoring system that keeps track of electricity flowing in the system. In this diagram, in smart grid, there are smart meters which tracks when consumers use electricity, which is more expensive during the usage hours. There are various components. One is smart meter, computer systems, the digital energy systems, which provide more efficient and reliable electricity to this grid. Okay, so these are unconventional energy sources which are basically connected to each other and generates the energy which is fed to the grid. Also, there are smart buildings or smart homes which has home energy sources which produces energy and it is again being supplied to the grid. Users view their energy usage in the real time from any computer and make the decisions about what is on or what is off while they are away. So if there is a peak time, so the electricity charges are more. So during those peak hours, basically the washing machine and other appliances need not be used uh, by the consumer. So consumer will remotely handle all those devices which are to be kept off during the peak hours. That means when the charge is high, the consumer will put it on when the charges are very low. So this is how basically smart grid system and smart home systems will work together by making use of IoT. Another application is cyber physical systems. So a cyber physical system is an embedded system which integrates the computing process with the physical world as an interactive and intelligent system. So cyber physical systems appear in many computer and TV game systems. The best example is the popular Nintendo Wii interactive gaming system. There are cursor-based CPSs which can be found in the automotive, aerospace, healthcare, robotics, manufacturing, battlefield training, and consumer appliance industries. A full-fledged CPS involves embedded computers, network monitors, and intelligent control of physical processes with humans in the feedback loop. Various components in which there is an embedded system which senses the data of the physical world. In a CPS, the cyberspace and physical worlds are intertwined. The embedded computing sense real world data. This embedded computing basically sense the real world data and it will be monitored through the human interaction. Another example in CPS is distributed robotic garden project at MIT. Researchers involved in a distributed robotic garden project at MIT have experimented on a set of robots to tend or maintain a garden of tomato plants. The system combines collaborative work in distributed sensing, navigation, manipulation, and wireless networking. The long term goal is to implement an autonomous greenhouse based on autonomous robots and sensors. The MIT research group envisions the following long term applications of their CPS work. So, one of the long term applications is the reduction of pesticides by the intelligent local combinations of the plants, reduce the water consumption, and uh, providing autonomous farming with a variety of products on a small scale in a fully autonomous fashion. Green architecture fruits and vegetables can be cultivated on the inside and outside of the buildings where they positively contribute to room climate and energy efficiency and support the inhabitants' diet. The next innovative applications of the IoT is online social and professional networking. So, online social networking enables many social and professional functions over the internet. For example, the websites such as Facebook, Twitter, LinkedIn, and MySpace, they provide the online services that allow users to create online profile pages and make friends with those who are registered on the same website or those with having the same interest or those which are located nearby region. Okay, so according to a recent global internet traffic report, there were almost 1 billion registered users among the top 15 social networks. So, one of the most popular social networks are Facebook and the Twitter, which is being used for microblogging and exchange of ideas. So, this is a table which summarizes the top 5 online social networks based on the number of registered users. So, this is the data. This is just for an indication that how the online social and professional networking works basically. So we have different applications of existing social networks in various domains. Like in business domain, we have LinkedIn. In education domain, we have National School Boards Association, and education topics can be researched online using this. We have Coursera, which has various education topics for the students. Khan Academy. We have Edureka. We have uh, there are many more. Like then in medical and healthcare as well, there's many different websites nowadays. One of the examples is Facebook. Sector-wise usage of, you can say, it was reported that 2.5 billion active users, making the Facebook one of the world's largest social network. This was the fourth quarter of 2019. The largest sector of applications to enhance the communications among the users. You can see from this particular pie chart that largest sector of applications is to enhance the communication amongst the user. Social selection, sending gifts, and profile enhancement facilitates more frequent social contacts. Tell me about me. Media sharing, playing, naming, dating, and social events are more traditional areas. There are various functionalities of Facebook features like profile page, social graph traversal, communication tools like email messaging. Then you can share the information with photo album. Then you can control the access. So every item on the profile page can be controlled. Okay, so which is to be whether to be shown to the friends, whether to be shown to the friends of friends, or whether to be shown the profile page to everyone or what. Okay, so basically this is the various functionality, and there are some special APIs for the same. So basically Facebook uses ringside social application server and their APIs. So this application server has APIs of its own, as well as they have also some APIs for Facebook. There are some APIs which are also being extended. So it is basically open source social application server which is implementing the APIs for Facebook as well. Okay, this is domain specific language. This is you can say Facebook markup language. Okay, which is being used for different tags which are generally used in in social networks. So it has open DSL, it has API, different APIs, and then this API uses different relationships, tags, profiles, and as well. So and the social and the open social integration. So the Facebook architecture built with the social engine servers and application programming interface. Twitter is another application of social networking. Uh, so Twitter is a microblogging service launched in 2006 by Jack Dorsey and others. So each message sent through Twitter can be no more than 140 characters in length. I think everybody knows about Twitter, what it is. So we'll just move next, that the architecture, how the architecture of Twitter and access control works. So there are three major components in Twitter system. One is crawler, another is indexer, and third one is searchers. Okay, the crawler sends a request to the Twitter API. The Twitter API responds with the Twitter data. The crawler stores the data into files. The indexer reads the stored files as input. The indexer stores the data in a database as output. Then user sends a search query to the searcher. So the searcher reads the data from the database and calculates a rank. The searcher reads the associated raw tweets and gives the result accordingly. So this is all about the unit number 5. So we have seen everything, whatever uh, is there available in the chapter. We, we have seen the cloud trends in supporting ubiquitous computing, performance of distributed system and the cloud, then enabling technologies for the Internet of Things. Then we have seen various innovative applications of the IoT. We have seen the example of smart building, smart power grid, then retailing and the supply chain management, then cyber physical systems, then online social and professional networking. So this is how we have completed the unit number 5. Thank you very much.